The physical universe imposes strict limits on human ambition, but occasionally a conceptual leap bypasses those limits entirely. In the mid-20th century, the ambition was limitless computation, but the physical limit was a tangled, insurmountable wall of wire. Engineers called it the tyranny of numbers. It was a paradox that threatened to strangle the digital age in its infancy, dictating that as machines grew more advanced, they simultaneously became too complex to actually build. To understand how we shattered this barrier, we must look at a dual independent invention that redefined the architecture of modern civilization. Following the Second World War, the invention of the transistor had already sparked a revolution. These small, solid-state devices replaced fragile, heat-generating vacuum tubes, promising a new era of electronic capability. Yet, a fundamental flaw remained in the system's architecture. Every individual transistor, along with every resistor and capacitor, still had to be manufactured separately and then wired together by human hands. It was a process of microscopic plumbing that was inherently doomed to fail at scale. The tyranny of numbers was a simple, brutal, mathematical reality. If a computer required 100,000 components to perform a complex calculation, it required hundreds of thousands of individual, hand-soldered connections. Even if a highly skilled technician achieved a 99.9% success rate in their soldering, a machine with that many connections would still possess hundreds of fatal flaws. The aerospace and defense industries were demanding guidance systems that could fit inside a missile cone, but the necessary wiring made them too heavy, too large, and critically unreliable. The solution to this insurmountable problem did not arrive in a flash of collaborative brilliance, but rather in the quiet isolation of a nearly empty laboratory. In the summer of 1958, a newly hired engineer named Jack Kilby found himself alone at Texas Instruments. Because he had not yet accrued vacation time, Kilby was forced to work through the company's traditional 2-week summer shutdown. It was within this quiet, uninterrupted space that he began to dismantle the fundamental assumptions of electronic engineering. Kilby recognized that the core issue was the diversity of materials. Factories were building transistors out of semiconductor material like germanium, but they were building resistors out of carbon and capacitors out of metal and glass. His foundational spark was a radical simplification. If a semiconductor could act as a switch, he theorized, it could also be manipulated to provide resistance and capacitance. He envisioned carving every necessary component out of a single, unified block of semiconductor material. This was the monolithic idea, a concept that sounded elegantly simple in theory, but was brutally difficult to execute in the laboratory. Kilby began experimenting with thin slivers of germanium, attempting to etch and manipulate the material to perform multiple distinct electrical functions simultaneously. The early experimental phase was a messy, imprecise process, relying on crude tools and a deep, intuitive understanding of solid-state physics to force the germanium to behave in entirely new ways. On September 12, 1958, Kilby stood before a group of executives at Texas Instruments to demonstrate his rudimentary creation. It was a phase-shift oscillator, roughly the size of a paperclip, consisting of a jagged piece of germanium with a few microscopic components carved into it, all connected by incredibly fine flying gold wires. When Kilby applied power, a perfect, continuous sine wave appeared on the oscilloscope screen. The first integrated circuit had just spoken its first words. The echoes of that foundational idea followed immediately, rippling through the scientific community. Kilby had successfully proven that the tyranny of numbers could be defeated not by building better automated soldering machines, but by eliminating the need for external wiring altogether. Yet his initial prototype, while conceptually brilliant, possessed a fatal flaw for mass production. Those flying gold wires, carefully placed by hand under a microscope, meant the circuit was still tethered to the very manual labor it sought to replace. Nearly 2,000 miles away in California, another brilliant mind was colliding with the exact same physical wall. Robert Noyce, a charismatic physicist and co-founder of Fairchild Semiconductor, was deeply aware of the interconnect problem. Noyce understood that Kilby's monolithic concept was the correct path forward, but he also recognized that a truly revolutionary technology needed to be seamlessly manufacturable. A chip that still required hand wiring was merely a laboratory curiosity, not an industrial revolution. The engineering challenge for Noyce was not just about putting components on a single piece of silicon. It was about figuring out how to connect them without human intervention. The breakthrough came from a colleague at Fairchild, Jean Hoerni, who had recently developed the planar process. This process involved leaving a protective layer of silicon dioxide on top of the silicon wafer, rather than etching it away, creating a flat, pristine surface that protected the delicate microscopic structures beneath. Noyce looked at Hoerni's flat, oxidized silicon surface and experienced his own foundational spark. He realized that this insulating layer of silicon dioxide could serve as a canvas. Instead of using flying gold wires, Noyce envisioned depositing microscopic lines of metal directly onto the oxide layer, etching them into pathways that would connect the underlying components. It was essentially printing the wiring directly into the chip's architecture, removing the human hand from the equation entirely. In early 1959, Noyce detailed this vision in his notebook, outlining a method to create a truly integrated circuit where both the components and their connections were manufactured simultaneously in a single, continuous process. The Fairchild approach was elegant, scalable, and perfectly suited for the burgeoning techniques of photolithography. It transformed the integrated circuit from a delicate, handcrafted artifact into a robust, mass-produced industrial product. This dual independent invention created a fascinating historical convergence. Jack Kilby had provided the fundamental conceptual break, proving that a monolithic circuit was possible. Robert Noyce had provided the vital manufacturing architecture, proving that it could be scaled and interconnected flawlessly. Two distinct approaches born from the same urgent technological bottleneck had arrived at a unified solution that would permanently alter the trajectory of human capability. The immediate aftermath of this dual discovery was not collaboration, but a fierce corporate conflict. Texas Instruments and Fairchild Semiconductor plunged into a bitter, protracted legal battle over the patents for the integrated circuit. For years, lawyers argued over the precise definitions of terms like monolithic and interconnect, fighting for control over a technology that both companies realized would soon become the foundational bedrock of the global electronics industry. However, the intellectual progression of the technology refused to wait for the courts to decide its ownership. The Cold War was escalating, and the United States government desperately needed the exact miniaturization that Kilby and Noyce had just invented. The military aerospace sector became the crucial catalyst, providing the massive influx of capital required to transform these early, unreliable prototypes into mission-critical hardware. The Apollo program and the Minuteman missile defense system served as the ultimate proving grounds. NASA needed a guidance computer lightweight enough to fly to the moon, but powerful enough to navigate the vastness of space. The early microchips were astronomically expensive and prone to manufacturing failures, but the government was willing to absorb the cost and the risk to achieve absolute technological supremacy. This guaranteed market allowed the nascent semiconductor industry to refine its processes. The manufacturing challenges during this era were staggering. Early clean rooms were primitive compared to modern standards, and a single speck of dust or a microscopic variation in temperature could ruin an entire batch of silicon wafers. Yield rates, the percentage of functional chips produced on a single wafer, were often in the single digits.
Engineers were operating at the absolute bleeding edge of chemistry, metallurgy, and optical physics, learning to manipulate matter at scales that were previously
unimaginable. Eventually, the corporate titans realized that their legal warfare was stifling the very market they sought to dominate. In a moment of pragmatic breakthrough, Texas Instruments and Fairchild Semiconductor agreed to cross-license their technologies. This pivotal compromise ended the patent wars and established a collaborative baseline for the entire industry. It acknowledged that the integrated circuit was too vast a concept to be hoarded by a single entity. It was a foundational platform upon which an entirely new ecosystem would be built. The echoes of that foundational compromise fueled an unprecedented era of rapid innovation. With the legal hurdles cleared, the industry coalesced around silicon as the standard substrate, validating Noyce's planar process while forever relying on Kilby's initial monolithic vision. Engineers began a relentless pursuit of miniaturization, shrinking the size of transistors and packing exponentially more computational power onto a single chip, a phenomenon that would soon be codified as Moore's Law. The unforeseen impact of this rapid scaling was a dramatic collapse in cost. Components that originally cost the military hundreds of dollars apiece soon plummeted to a few dollars and eventually to fractions of a penny. This economic deflation allowed the integrated circuit to escape the highly classified confines of aerospace engineering and infiltrate the commercial market. The technology that was designed to guide nuclear missiles was suddenly powering pocket calculators and digital watches. This transition from military hardware to consumer electronics fundamentally reshaped society. The microchip became the silent engine of a new digital reality, enabling the creation of the personal computer, the mobile phone, and the sprawling infrastructure of the global internet. The complex, room-sized mainframes of the 1950s were rapidly replaced by devices that could fit in the palm of a hand, democratizing access to information and computational power on a planetary scale. Looking back at the raw, first versions of this technology, the intellectual awe lies in the sheer audacity of the vision. Kilby's messy germanium sliver with its flying gold wires and Noyce's elegant flat silicon architecture seem impossibly primitive compared to modern processors containing tens of billions of transistors. Yet, every single modern microchip, no matter how advanced, is a direct, unbroken descendant of those initial experiments in 1958 and 1959. The genesis of the integrated circuit reveals a profound truth about the nature of technological leaps. They rarely occur in a vacuum, and they are almost never the result of a single, isolated genius. They are born from a confluence of urgent necessity, parallel thinking, and the willingness to fundamentally question the established rules of engineering. Kilby and Noyce did not just invent a new component. They invented a new way of organizing complexity. They proved that the physical limitations of the universe can sometimes be outmaneuvered by a shift in perspective. By looking at a tangled web of wires and seeing instead a solid, unified block of potential, they bypassed the tyranny of numbers entirely. Their dual independent invention stands as a testament to human ingenuity, a reminder that the most profound breakthroughs often require us to stop trying to improve the existing system and instead to reinvent the very fabric of the machine. Today, as we stand on the precipice of quantum computing and neural architectures, the foundational lessons of the microchip's origin remain acutely relevant. We are once again facing walls of complexity and physical limits, searching for the next monolithic leap that will redefine our capabilities. The quiet laboratories of Texas and California may be decades in the past, but the intellectual spark they ignited continues to illuminate the furthest edges of future tech and science. The story of Jack Kilby and Robert Noyce is not merely a chapter in the history of electronics.
It is the definitive genesis point of the modern world. It is a narrative of how two men, separated by geography but united by a singular, insurmountable problem, managed to etch the future of humanity onto a microscopic sliver of stone. Their foundational impact is embedded in every screen we touch, every calculation we run, and every digital connection that binds our world together.